The morning of June 6, 1944. Omaha Beach, 5:30 a.m. The ramp drops on landing craft number 47, and 36 men pour onto blood-soaked sand under a hail of German machine gun fire. But here's what the grainy newsreels never captured. This moment, this exact sequence of events, drop the ramp, troops sprint onto dry beach, reverse off in 30 seconds, was supposed to be impossible. Every naval architect in America had said so. Every established shipyard had submitted technical papers, proving it violated fundamental laws of physics and marine engineering. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Yet there it was, happening every 3 minutes, boat after boat after boat. A mechanical conveyor belt of steel and diesel fuel that transformed the mathematics of amphibious warfare from theoretical suicide into brutal, grinding reality. The plate. Germans weren't just fighting soldiers that morning. They were fighting a production system designed by a man who'd never attended a single day of naval architecture school, who'd spent his career building boats for Louisiana swamp trappers and rumrunners, and who had the infuriating habit of being right when everyone with advanced degrees insisted he was wrong. Let's rewind to September 1941. The United States Marine Corps has just posted a technical requirement that reads like science fiction. They want a boat that can carry 36 combat-loaded troops, or a jeep with crew, approach a hostile beach at full speed, drop those troops onto dry sand in under 10 seconds, then reverse off and return for another load, all in under 15 minutes round trip. The specifications continue. Draft shallow enough to clear coral reefs, stable enough to survive open ocean crossings, cheap enough to build by the thousands, simple enough that 19-year-old coxswains with minimal training could pilot them under artillery fire. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Marine Corps sends these specifications to every major shipyard in America: Newport News Shipbuilding, Bath Iron Works, New York Shipbuilding Corporation. These are companies with pedigrees stretching back to the 1800s, firms that built battleships and luxury liners, employing thousands of master craftsmen who learned their trade through decade-long apprenticeships. Their response is unanimous: impossible. The technical objections fill 3 ring binders. A hull shape shallow enough for reefs cannot be stable in open ocean. The physics contradict each other. A bow ramp strong enough to support running troops and vehicles would be too heavy. The boat would be bow-heavy and unstable. The hydraulics would fail in salt water within days, even if you solved the ramp. Problem: the boat couldn't extract itself from the beach. Propellers would foul on sand. The hull would ground out. But there's this one guy, down in New Orleans, keeps showing up at Navy procurement offices in Washington with a wooden model and a grin that suggests he's already solved the problem. The procurement officers are polite but dismissive. The technical bureaus file his proposals under eccentric civilian submissions. He doesn't have blueprints drawn to Navy standards. He doesn't have a degree from MIT or the Naval Academy. What he does have is 30 years of experience building shallow draft boats that can navigate through Louisiana bayous, where the water is 18 inches deep and full of cypress knees that would shred a conventional hull in minutes. His name is Andrew Jackson Higgins. Born in Nebraska in 1886, he's spent 3 decades figuring out how to make boats do things that marine engineering textbooks say they can't do. While Naval Academy graduates were designing sleek destroyers with deep keels and sharp bows, Higgins was building flat-bottomed workboats for oil prospectors, trappers, and, during Prohibition, the occasional rum runner who needed to outrun Coast Guard cutters through shallow coastal waters. His company, Higgins Industries, operates out of a facility in New Orleans that looks nothing like a proper shipyard. No massive gantry cranes, no enclosed building sheds, just open work areas where men assemble boats using techniques Higgins developed through trial and error in the swamps. The boats look wrong to trained eyes. The bows are flat and wide, shaped like snow shovels. The hulls have almost no keel, just a shallow tunnel protecting the propeller. Everything about them violates conventional naval architecture. But they work. In 1938, some junior Marine Corps officer remembered hearing about this crazy Cajun who built boats that could run on heavy dew, as the saying went. The Marines, desperate for any solution to their landing craft problem, sent observers to New Orleans, mostly to check a box, mostly to say they'd investigated every option, no matter how unlikely. Higgins loaded them into his latest design, a boat called the Eureka, and proceeded to drive it full throttle onto a mudflat. The observers braced for impact, expecting the boat to ground out and stick. Instead, Higgins spun it around like a sports car and motored back into deep water. Then he did it again, and again, 20 times without fouling the propeller or damaging the hull. The observers sent a cable to Marine Corps headquarters. You need to see this immediately. Here's what made Higgins's design revolutionary, and why it enraged every established naval architect who examined it. Traditional wisdom held that a boat's bow should be sharp to cut through water efficiently. Hydrodynamic theory, developed over centuries, specified V-shaped hulls that minimized drag. Higgins built a bow shaped like a flat plate, angled upward at 45 degrees. Maximum drag, terrible efficiency by conventional standards. Traditional wisdom required a deep keel for stability. Every textbook on naval architecture explained that keels provide the lateral resistance necessary to prevent a boat from sliding sideways in currents or waves. Higgins's boats had almost no keel, just a shallow semi-tunnel that barely protruded below the hull, designed solely to protect the propeller from obstacles. The Bureau of Ships, the Navy's technical authority on all matters maritime, produced lengthy papers explaining why the Eureka's design violated fundamental hydrodynamic principles. The flat bow would create excessive drag, reducing speed and increasing fuel consumption. The lack of keel would make the boat uncontrollable in cross-currents. The shallow draft would cause the boat to pound violently in waves, damaging the hull structure. Higgins invited Bureau engineers to New Orleans for demonstrations. They declined, citing budget constraints. Translation: We're not wasting taxpayer money watching some swamp boat builder embarrass himself when serious companies are developing proper solutions. But the Marines kept pushing, because unlike the desk admirals in Washington, the Marines would actually have to storm beaches. They understood that theoretical elegance meant nothing if boats couldn't get troops ashore alive. In April 1941, the Navy finally agreed to competitive trials in Norfolk, Virginia. 4 shipyards presented designs. 3 came from established maritime companies with gilt-edged reputations and government contracts stretching back decades. Higgins showed up with 3 boats strapped to a barge. No formal presentation, no technical drawings rendered in Navy standard drafting format, just hardware. The evaluation criteria included seaworthiness, speed, maneuverability, durability, and the critical test, ability to extract itself from a beach after grounding. The trials ran for 3 days. By the end of day 1, the outcome was clear. By day 3, Navy observers were quietly rewriting procurement protocols. Higgins' boats hit the beach at 9 knots, rode up onto sand, backed off in under 30 seconds, and repeated the maneuver. 20 consecutive runs, without fouling the propeller or damaging the hull. The competition? 1 boat buried its bow on the first attempt and wouldn't budge. Sailors had to dig it out. Another's propeller shattered on contact with sand. The third made it on and off once, then started taking on water through stress fractures. By the end of day 2, Admiral Ernest King, Commander-in-Chief of the U.S. Fleet, was receiving hourly updates. By day 3, Higgins had a contract for 1,500 boats, and he still hadn't shown them his actually revolutionary idea yet. The Eureka solved half the problem, getting to the beach, getting off again. But troops still had to scramble over the sides into knee-deep water, and there was absolutely no way to drive a jeep off the boat. The gunwales were 4 feet high. You'd need a crane. Higgins knew this. He'd been sketching solutions for 2 years. Every design hit the same wall. Physics. A ramp at the bow meant hinges. Hinges meant a weak point where the boat flexes most, right at the bow where waves hit hardest. Picture a steel plate 4 feet wide, 8 feet long, holding up 6 men weighing 250 pounds each with full combat gear, while the boat pitches in 3-foot swells. That's 1,500 pounds bouncing on a hinge mechanism every 2 seconds. Navy engineers calculated the stress loads. Any hinge strong enough would be too heavy. Any hinge light enough would snap within a week of saltwater operations. Then, in late 1941, a Marine Corps officer named Victor Krulak showed Higgins a photograph that changed everything. Krulak had been an observer in Shanghai in 1937, watching Japanese forces assault Chinese positions along the Yangtze River. The photograph showed a Japanese Daihatsu-class landing craft with a ramp at the bow, not over the sides. A ramp. Higgins stared at that image for maybe 10 seconds. Then, according to witnesses, he said something unprintable about how the Japanese had the right idea but the wrong execution. Because their ramp still made troops wade through ankle-deep water. Here's where 30 years of swamp boat experience kicked into overdrive. The Japanese design dropped a ramp that angled down into the water. Fine for calm rivers, useless for surf zones where every wave changes depth by 2 feet. Higgins realized the ramp couldn't just drop. It had to drop and extend forward, creating a bridge from the boat deck to dry beach. The geometry sounds simple, until you actually try building it. The ramp needs to match the bow angle, 45 degrees in Higgins' design. When raised, it becomes the bow itself, a watertight continuation of the hull. When lowered, it must lock flat and stable enough that a 5,000-pound Jeep can drive across it at speed without flexing more than half an inch. His solution was pure mechanical brutality. 2 hydraulic cylinders pulling steel cables, backed up by manual chain drives in case hydraulics failed. The ramp itself was 1/4-inch steel plate, reinforced with I-beams welded underneath, heavy as hell. But that weight actually helped. Once it slapped down on sand, momentum and mass kept it planted. The hinges weren't delicate pivot points. They were massive pin assemblies, 4 inches in diameter, the kind you'd use on a drawbridge. Could they fail? Absolutely. But they'd survive long enough to matter. And Higgins designed the entire mechanism so a crew could replace a broken hinge in 20 minutes with a sledgehammer and a cheetah bar. The first prototype was ready in May 1942. Higgins called it the LCVP. Landing craft, vehicle, personnel. The military called it the Higgins boat, though Andrew hated that name. He wanted credit going to his engineers. The Marine Corps brought it to Solomon's Island, Maryland, for testing. The evaluation team loaded it with a full platoon plus a jeep, something no landing craft in the world could do. They motored to a beach and watched. Ramp down. Jeep off in 4 seconds. Troops off in 6 more. Ramp up. Reverse into deep water. 13 seconds total from grounding to withdrawal. The officer running the test radioed Washington. Specifications met. Recommend immediate mass production. 3 weeks later, Higgins had a contract for 10,000 units. The Pentagon still thought the design would fail in actual combat. But by mid-1942, German U-boats were sinking, Allied shipping faster than it could be replaced, and Japan controlled half the Pacific. Desperation makes excellent fertilizer for innovation. The military placed the order knowing that if Higgins was wrong, thousands of Marines would die on beaches. If he was right, they might actually win the war. Dwight D. Eisenhower said it years after the war, and the quote deserves to be carved in marble somewhere. Andrew Higgins is the man who won the war for us. If Higgins had not designed and built those landing craft, we never could have landed over an open beach. The whole strategy of the war would have been different. Coming from a 5-star general who commanded the largest amphibious invasion in human history, that's not hyperbole. It's mathematical fact. But let's examine the actual numbers, because the reality is somehow more insane than the legend. Guadalcanal, August 7th, 1942. First major combat test of the Higgins boat under hostile fire. The 1st Marine Division needed to land 11,000 troops on beaches defended by 2,800 Japanese soldiers who'd had months to prepare fortifications. Pre-war doctrine, based on experience from World War I and theoretical studies, estimated this operation would require 14 to 18 hours to get everyone ashore with equipment. The actual timeline: 4 hours and 17 minutes from first boat hitting sand to last rifle company digging in. Marine logistics officers thought their stopwatches were broken. They radioed the transport ships offshore. Confirm troop counts. This can't be right. The transports confirmed. Every man accounted for. Plus 73 vehicles that doctrine said couldn't possibly be landed on day one. Here's the mechanical magic that made it possible. A single Higgins boat could complete the beach to transport run in 11 to 15 minutes, depending on distance. That's grounding, unloading, reversing, motoring back to the ship, and reloading. Compare that to British landing craft at Dieppe 3 weeks later, which averaged 32 minutes per cycle, and couldn't extract themselves, leaving dozens stranded as the tide went out, becoming stationary targets. At Guadalcanal, the Marines had 87 Higgins boats in the first assault wave. Simple mathematics. 87 boats times 4 trips per hour equals 348 boatloads delivered every 60 minutes. Each boat carried 36 men or 1 vehicle with crew. Run that arithmetic and you get over 12,000 personnel equivalent movements per hour. The bottleneck wasn't the boats, it was how fast sailors could load them on the ship side. Some transport crews got so efficient they were loading a boat every 45 seconds. Troops would climb down cargo nets while the previous boat was still pulling away. The moment it cleared, the next boat would slide into position. Tarawa. November 1943. This is where the 3-minute claim gets tested under nightmare conditions. The Navy's hydrographic charts were wrong. The tide was 18 inches lower than predicted. A coral reef extended 500 yards from shore. Larger, landing ships, LSTs designed to carry tanks, grounded out on that reef and couldn't budge. Their ramps dropped into 4 feet of water, which meant tanks couldn't disembark without drowning their engines. But the Higgins boats, drawing only 3 feet of draft when loaded, skimmed right over that reef like it wasn't there, wave after wave. Every 3 to 4 minutes, another boat hit Red Beach. The Japanese defenders had pre-sighted machine guns and mortars on the waterline, expecting slow-moving targets bunching up in predictable locations. Instead, they got a conveyor belt. The Marines took horrific casualties, over 1,000 dead in 76 hours, but they kept coming because the boats kept running. Japanese commander Keiji Shibasaki had boasted it would take 1 million men 100 years to conquer Tarawa. The Marines did it in 3 days, largely because Higgins boats delivered reinforcements faster than defenders could kill attackers. The mathematics of attrition had shifted. In previous amphibious assaults throughout history, defenders held the advantage because attackers arrived in predictable waves with long pauses between. Defenders could recover, reposition, bring up reserves. At Tarawa, there were no pauses. The 8th wave hit the beach, while defenders were still fighting the 5th wave. The 15th wave arrived before Japanese officers could even assess the situation. Sicily, July 1943. Operation Husky involved 2,590 landing craft of all types, hitting 26 beaches simultaneously. Higgins boats made up about 1,400 of that total. The operational tempo was surgical. Boats grounded, unloaded, withdrew, and returned with such mechanical rhythm that beachmasters were spacing arrivals like air traffic controllers. Some boats made 14 round trips in the first 12 hours. Crews worked past exhaustion, steering by instinct, loading by muscle memory. When Navy analysts compiled after-action reports, they found the average Higgins boat at Sicily delivered 468 troops, or 23 vehicles, over 3 days of continuous operation. Multiply that across 1,400 boats, and you understand why German forces couldn't reinforce fast enough to mount effective counterattacks. Then came Normandy. June 6, 1944. Over 1,500 Higgins boats in the initial assault waves, across 5 beaches. Utah Beach logged boats arriving every 3.2 minutes during peak hours. The flow was so consistent that Navy officers coordinated timing with stopwatches. Omaha Beach was chaos. German defenses were far stronger than intelligence had predicted. The terrain was worse. The fortifications more extensive. But even there, even in the sector where nearly everything went wrong, the boats never stopped coming. That's what broke the German defense. Not heroism alone, though there was plenty of that. Not superior tactics. The boats made that grinding persistence possible. You can kill the first wave, even the second. But the 8th wave? The 15th? When boats keep hitting the beach every 3 minutes for 8 straight hours, when reserves keep arriving faster than you can count them, when ammunition and supplies flow ashore in continuous stream, defenders break. Not because they lack courage, because mathematics overwhelms courage. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Now here's a question that haunted Allied intelligence officers throughout the Pacific Campaign. The Japanese invented the bow ramp concept. Their Daihatsu-class landing craft pioneered it back in the 1930s during operations in China. They had the photograph that inspired Higgins. So why didn't they build something as effective as the Higgins boat? Every time US forces captured a Japanese-held island, they found Daihatsu craft that almost worked but fell short in critical ways. The answer reveals something fascinating about how engineering philosophy shapes wars. The Daihatsu, first deployed in 1937 during the Second Sino-Japanese War, looked superficially similar to Higgins's design. Bow ramp, shallow draft, ability to beach and retract. But Japanese engineers had optimized for completely different conditions. Their primary operations were along rivers and calm coastal waters in China and Southeast Asia, places where you could predict tides, survey beaches in advance, operate in relatively protected waters. The Daihatsu had a deeper V-hull for efficiency in calm water, which made it faster in ideal conditions but absolutely terrible in surf. When waves hit that V-hull at an angle, the boat would skew sideways, sometimes capsizing entirely. Marines reported watching Daihatsu craft flip in 3-foot swells that Higgins boats handled easily. The ramp mechanism tells the whole story. Japanese designers used a lightweight ramp that dropped down into the water at a steep angle, perfectly adequate for a riverbank with 6 inches of water, but hit a beach with 2-foot surf, and troops still had to wade through knee-deep water, losing speed, losing surprise, getting shot. Marines captured Daihatsu craft at Guadalcanal and tested them extensively. The official assessment was brutal. Ramp does not extend hull line. Vehicle operation impossible in surf conditions. Extraction from beach inconsistent due to underpowered engines and hull design unsuitable for backing off under load. Here's the deeper mistake. The Japanese never understood that Higgins's ugly, blunt bow wasn't a design compromise. It was the entire point. That snow shovel shape let the boat ride up onto the beach at speed, using momentum to climb sand until the ramp could drop onto dry ground. The Daihatsu's sharper bow would dig into sand and stick. Japanese crews compensated by approaching more, slowly, which gave defenders more time to aim. At Tarawa, US forces found abandoned Daihatsu craft that had beached successfully but couldn't reverse off. The propellers had hit coral, or the hull had settled too deep into sand. They'd become stationary bunkers instead of transportation. The Imperial Navy did eventually try to copy Higgins' boats directly. In 1944, Japanese engineers examined captured LCVPs from the Philippines and produced detailed specifications for a domestic version. But by then, Japan's industrial capacity was collapsing under American bombing. They had the blueprints, but lacked the manufacturing infrastructure to produce complex hydraulic systems in quantity. More critically, they didn't have the shipyard workforce. Higgins Industries employed semi-skilled laborers who learned to weld hull sections in weeks, not years. Japan's traditional shipbuilding culture relied on master craftsmen, which doesn't scale when you need thousands of boats immediately. There's a captured Japanese naval assessment from late 1944 that's almost tragic to read. The author, an engineering officer, wrote that American landing craft demonstrated crude but effective design principles that sacrificed elegance for mass production and rough water performance. He noted that US boats could be crewed by experienced personnel because the controls were simple and the hull forgave operator errors. Japanese landing craft required skilled coxswains to handle properly. In his conclusion, the officer wrote that Japan had focused on quality when the Americans understood the war would be won by quantity, and that fundamental philosophical difference couldn't be reversed by copying a hull shape. By 1945, Japanese forces across the Pacific were still using Daihatsu craft that required troops to jump into water. Meanwhile, every US amphibious assault had become a textbook example of mechanized efficiency. The Japanese had invented the bow ramp, but never realized its full potential. Higgins took their idea, understood what it should do, and rebuilt it from first principles. That's not just copying. That's evolution through understanding. August 7th, 1942. Back to Guadalcanal, because theory was about to slam face first into coral, Japanese machine guns, and the kind of chaos that makes engineering textbooks look adorable. The Higgins boat had performed beautifully in calm water tests at Norfolk and Solomon's Island, but those were controlled environments with measured beaches and no one shooting back. Now 87 boats were heading toward Lunga Point carrying the 1st Marine Division, and absolutely nobody knew if the design would hold up under actual combat stress. First problem, the reef. Pre-invasion reconnaissance had spotted it, but intelligence underestimated how far it extended and how shallow the water got. Larger landing ships grounded out 400 yards from shore and stuck fast. Higgins' boats, drawing just 3 feet when loaded, skimmed over with inches to spare. Coxswains reported feeling the hull scrape coral, hearing that sickening grinding sound, but the boats kept moving. Higgins had over-engineered the hull bottom, double-riveted seams, reinforced keel guards, specifically because he assumed boats would hit things. That paranoid design approach saved the landing in the first 30 minutes. Second problem, beach composition. The sand at Lunga Point wasn't the firm, packed type from test ranges. It was loose volcanic material that shifted under weight. When the first boats hit at full speed, their bows dug in deeper than expected. Some buried 18 inches before momentum stopped. Crews panicked, thinking they were stuck. Then the ramp hydraulics kicked in. The weight of the dropping ramp actually helped level the boat, redistributing mass forward. Troops ran off, the boat lightened by 7,000 pounds, and coxswains gunned the tar, engines in reverse. Most extracted in under 40 seconds. A few needed second attempts, backing off at an angle to break suction. Third problem, enemy fire. This is where mechanical simplicity paid off in ways no one anticipated. Japanese defenders targeted the boats with mortars and machine guns. Bullets punched through the plywood gunwales. Higgins used plywood for the sides to save weight, with steel only on the ramp and hull bottom. Troops crouched behind the ramp for protection, which worked because that quarter-inch steel could stop rifle rounds. But here's the critical part. When hydraulic lines got severed by shrapnel, which happened to 11 boats in the first wave, crews switched to manual chains, 2 men cranking handles. The ramp dropped in 18 seconds instead of 6, but it still dropped. That redundancy, hydraulic primary with manual backup, meant damaged boats kept functioning. Fourth problem, sustainment. Over the next 3 days, those 87 boats ran continuously. No maintenance facilities, no replacement parts, just crews performing field repairs between runs. They used seawater as coolant when fresh water ran out. They patched bullet holes with tar and canvas. One boat lost its entire hydraulic system to a mortar fragment. The crew operated it manually for 2 full days, 23 trips, until a repair ship arrived. Higgins had designed every major component to be replaceable with hand tools and brute force. Propeller damaged? Carry a spare and swap it in 20 minutes. Ramp, hinge, cracked? Bolt on a backup plate and keep running. The after-action reports from Guadalcanal filled 3 binders. Navy maintenance teams inspected every boat after the first week. They found stress fractures, worn bearings, corroded fittings, but no catastrophic structural failures. The average boat had grounded 31 times, taken multiple hits, operated in salt water without maintenance, and was still 87% mission capable. Engineers had predicted a 40% failure rate within the first 48 hours of combat operations. The actual failure rate was 9%, and most of those were boats that took direct hits from artillery. Guadalcanal didn't just validate the Higgins boat. It proved that unglamorous, overbuilt, idiot-proof design beats elegant engineering when people are trying to kill you. Here's where the story gets completely unhinged. In December 1941, Higgins Industries was a regional boat shop employing 75 people, building maybe a dozen craft per month. By December 1944, it had become the largest private employer in Louisiana, with over 20,000 workers, operating 7 plants spanning 30 city blocks, and delivering 700 boats monthly. That's not scaling production, that's industrial sorcery. Andrew Higgins pulled it off by breaking every manufacturing rule the government insisted was sacred. The military's procurement office had very specific ideas about how shipbuilding should work. You hire trained shipwrights who've spent years learning the craft. You build boats one at a time, start to finish, with the same crew seeing each vessel through completion. You maintain strict quality control, with inspectors signing off at each stage. Higgins looked at that model and said, "That's adorable, but we need 20,000 boats in 3 years. Watch this." He borrowed a trick from Henry Ford that the maritime industry considered heresy: assembly line production. Boats don't move through factories, shipbuilders insisted. Higgins made them move anyway. He broke LCVP construction into 14 major sub-assemblies. Station 1 fabricated the bow ramp and hydraulics. Station 2 built hull sections. Station 3 handled engines and drive systems. Workers specialized in one task: welding a specific seam, riveting a particular joint, wiring one electrical system. A kid from rural Louisiana who'd never seen the ocean could learn to weld a perfect hull seam in 2 weeks. The traditionalists screamed that this would produce inferior boats. Higgins's response was to invite Navy inspectors to test random boats off the line. The failure rate was 2.1% better than traditional shipyards producing one-off vessels with master craftsmen. The workforce itself became revolutionary. Higgins hired anyone who could hold tools: women, black workers, elderly men past draft age, even teenagers on summer break. In 1940s New Orleans, this was radical. The company integrated its factories years before the military integrated its units. Black and white workers shared the same assembly lines, ate in the same cafeterias, used the same bathrooms. Higgins's reasoning was pure pragmatism. I don't care if they're purple with pink polka dots. Can they weld? But the social impact was profound. By 1943, 18% of his workforce was black and 40% was women. Rosie the Riveter wasn't just a poster in New Orleans. She was building the boats that would win the war. The production tempo was relentless. In June 1944, the month of D-Day, Higgins Industries delivered 737 landing craft. That's 24 boats per day. 1 boat every 60 minutes, working 3 shifts around the clock. The plants never stopped. Welding arcs lit up the night sky like continuous lightning storms. Workers clocked 60-hour weeks as standard, with 80-hour weeks common before major invasions. The company paid premium wages, $1.20 per hour, when the national average was 65 cents, because Higgins understood that, exhausted, broke workers build bad boats. Well-paid, motivated workers could maintain quality while hitting insane quotas. Raw materials became the bottleneck, not labor. A single LCVP required 1.2 tons of steel plate, 80 feet of hydraulic line, 340 rivets, 15 gallons of marine paint, and one 225 horsepower grey marine diesel engine. Multiply that by 700 boats monthly, and you need 840 tons of steel, 56,000 feet of hydraulics, 238,000 rivets every month. On time. No exceptions. Higgins established direct relationships with steel mills in Pittsburgh, rubber plants in Akron, engine manufacturers in Detroit. He bypassed military logistics entirely when procurement officers moved too slowly, sometimes purchasing materials on the private market at higher cost just to maintain delivery schedules. The Pentagon hated this cowboy approach until they realized boats kept showing up exactly when promised. By war's end, Higgins Industries had produced 20,940 boats, not just LCVPs, but also larger LCMs, PT boats, and specialized craft. That's more than all other American boat manufacturers combined. The company accounted for 92% of the Navy's landing craft fleet. When Japan surrendered in August 1945, Higgins had orders for 12,000 additional boats that were instantly cancelled. Within 6 months, the workforce dropped from 20,000 to 800. The empire collapsed as fast as it had risen. But those 20,000 boats had already rewritten military history. Omaha Beach, 06:30 hours, June 6, 1944, the most famous 6 hours in amphibious warfare history. Higgins' boats were the thread holding the entire invasion together. When you watch those grainy films or Hollywood recreations, you're seeing the culmination of everything: the design evolution, the manufacturing miracle, the combat testing. But you're also seeing the blueprint that every amphibious assault for the next 80 years would follow, right down to today. The numbers from Normandy are staggering in a way that doesn't fully register until you slow down and think about the logistics. The initial assault waves used 1,089 Higgins boats across 5 beaches. At Omaha alone, 293 LCVPs made the run from transport ships to shore. Each boat cycled an average of 4.7 times in the first 12 hours. That's 1,377 individual beach landings at one location in half a day. Picture a boat grounding, unloading, and extracting every 31 seconds during peak hours. The German defenders weren't just fighting soldiers. They were fighting a mechanical system designed to overwhelm them through sheer repetition. Even when boats took direct hits, 34 were destroyed at Omaha by obstacles, mines, and artillery. The flow barely slowed because replacements kept coming. The doctrine that emerged from Normandy became scripture. Modern amphibious operations still follow the Higgins template. Waves of landing craft, timed intervals, continuous resupply. Vehicles landing directly onto beaches. The U.S. Marine Corps' current landing craft air cushion, those hovercraft that look like science fiction, operationally functions the same way as an LCVP, faster, more sophisticated. But same core mission: deliver troops and vehicles from ship to shore, then get out and do it again. The Chinese People's Liberation Army Navy studied Normandy footage when designing their Type 726 landing craft for potential Taiwan operations. The underlying geometry hasn't changed. Protected run-in, bow ramp, rapid egress. But here's what often gets forgotten in the celebration of D-Day. The Higgins boat's impact went far beyond Europe. In the Pacific, the island-hopping campaign was essentially a Higgins boat conveyor belt, spanning 5,000 miles. Guadalcanal, Saipan, Peleliu, Iwo Jima, Okinawa. Each operation depended on those shallow-draft workhorses running through coral reefs that would have stopped conventional landing ships. At Iwo Jima, in February 1945, Marines landed 30,000 troops in the first 48 hours, using 482 Higgins boats operating on beaches with volcanic ash so loose that vehicles sank to their axles. The boats adapted. Coxswains learned to hit the beach at higher speeds, using momentum to climb above the worst sand. That operational flexibility, the ability to adjust technique based on conditions, came from the design's fundamental simplicity. Andrew Higgins died in 1952, 7 years after the war ended, largely forgotten and nearly bankrupt. His company never transitioned successfully to peacetime production. Military contracts evaporated, and he'd leveraged everything to meet wartime quotas, leaving no financial cushion. The man Eisenhower credited with winning the war spent his final years fighting predators. There's no Higgins Memorial on the National Mall. No aircraft carrier named in his honor. Most Americans have never heard his name. But if you've watched any footage of beach landings, World War II, Korea, Vietnam, Gulf War, Iraq, you've seen his legacy. Every ramp that drops onto sand traces back to that swamp boat builder who convinced the Pentagon that ugly and practical beats elegant and useless. The modern US military still operates landing craft directly descended from Higgins's design. The landing craft utility can trace its lineage through 7 evolutionary steps back to the LCVP. When Marines hit the beach in training exercises at Camp Pendleton or Quantico, they're executing procedures written in 1943 based on Higgins' boat capabilities. The doctrine assumes you can deliver troops and vehicles directly onto contested beaches in measured intervals, an assumption that only became possible because one engineer in New Orleans refused to accept that it was impossible. Wars get won by tanks and aircraft and brave soldiers, but sometimes they get won by a glorified swamp boat with a ramp on the front. Eisenhower understood that. The rest of us should too. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.